Hello everyone, our project is about reinforcement learning on HKUSTurkey. This is our team member introduction. Reinforcement learning is a hot topic these days. It can be applied to many different disciplines, such as game theory, control theory, simulation-based optimization, etc. And the content consists of 4 parts in this presentation: project introduction, reinforcement learning, Q-learning, and project result. This is a project about maze-solving problem. In this project, we are going to apply the technique of reinforcement learning to train the turkey in the maze to find the logo of HKUST. We have 2 goals for this project. The first one is to train the turkey to find the HKUST logo in the maze, and the second one is to find the optimized path for solving this problem. Reinforcement learning is a branch of machine learning that is concerned with how learners perform tasks by taking actions in an environment so as to maximize a numerical reward signal. And this is an illustration about the system of reinforcement learning. The key concepts have state, reward, action, and environment. A reinforcement learning agent interacts with its environment in discrete time steps. At each time t, the agent receives an observation which typically includes RT. It then chooses an action AT from the set of available actions, which is later sent to the environment. The environment moves to a new state ST+1 and the reward RT+1. The goal of reinforcement learning is to collect as much reward as possible.
Let me introduce the concept about the Q-learning. First, there is an example. The example describes an agent which uses unsupervised learning to learn about an unknown environment. Suppose we have 5 rooms in a building connected by doors as shown in the figure. We number the rooms from 0 to 4. The outside of the building can be thought as one big room 5. Then we can present the rooms in this graph. That is, each room has a node and each door has a link. We put an agent in any room, and the agent needs to go outside the building. So there is a reward value to each door. The doors that lead immediately to the goal have 100 reward, and other doors not to the target room have 0 reward, just in the right graph. Suppose an agent in room 2, and we want the agent to learn to reach outside the room 5. We can put the state diagram and the reward values into a reward table, which is a metric. Then, the agent starts training and updating through the experience. Within the function below, the agent can explore from its state until it reaches the goal. And if the agent learns more through further epochs, it will finally reach convergence values in the metric Q shown here. Here is a Q-learning algorithm. Q-learning chooses and performs an action and measures the reward to update the Q table again and again to try to maximize the reward. Let's move to our project applications. Our goal is training the turkey in the map that can automatically find the optimal path to the HKUST logo. In the simple map, the logo turkey represents the agent, and the typhoon is the barrier, and the HKUST logo is our final destination. For the applications in the reinforcement learning, the state here is to use the coordinates of the turkey in the maze to present the state. The actions of the agent that the turkey can go up, down, right, and left. The rewards are shown here. The turkey gets -30 when it meets the typhoon, and -10 reward happen when the turkey hits the wall. When the turkey finally gets the destination, there is +15 reward. In other cases, the reward is -0.1. In this case, the turkey can find the optimal path. Here is our final performance. The graph shows that after many epochs, the agent can find the optimal path with high rewards. At the same time, the time for each epoch is decreasing. So finally, we use math algorithm to set a math, and after almost 35 epochs, the turkey can find the best route.
Let's go deeper about the Q-learning. Recall that this is a model-free approach. It means that we did not need to collect any information of the environment, but we have to build a table of utility value as the agent interacts with the environment. So let's suppose we already have the optimal Q table. The vertical coordinate represents the state we are looking at, and the horizontal coordinate represents the action we may take. The value helps us to use to select the best action based on what it has learned so far. And the important thing to know is that Q is not greedy, in the sense that it not only represents the reward you get from acting now, but also represents the reward you get from acting in the future. The next question is how we build a Q table. We first initialize all the QSA to 0 and then we do the update rule. The new value of QSA consists of two parts, the old QSA value and the improved estimation. And how to combine them? We use the learning rate alpha. The larger value of alpha causes us to learn more quickly, and a low value of alpha causes the learning to be more slow. So, a low value of alpha, for instance, means that in this update rule, the previous value of QS8 preserved more strongly. And next, we'll stretch this expression a little bit in detail. Here is the gamma rate, and also we call it the discount rate. A low value of gamma means that we value later reward less, and a high gamma, nearly 1, means that we value the later rewards very significantly. After we run the Q-learning for long enough, we will eventually converge to the optimal policies. The third question is how to choose an action. We want the agent makes the best choice at each step, but here's some problem. We don't have the accurate Q value at the beginning, and the agent does not exploit the environment efficiently. In the reinforcement learning, the exploit and exploit is the key. So we introduced the epsilon gradient algorithm to improve the policies while ensuring that we exploit the environment. Here we set the epsilon to 0.3, and each time we choose an action, we generate a number between 0 and 1. If the number is less than epsilon, we choose an action randomly, otherwise, we choose the action according to the maximized rule. So let's welcome my partner to introduce the implementation part.
Okay, then I'm going to introduce the implementation of our project, including the code and files. There are 3 files in our project, mains, turkey, and runner. The mains and turkey class is the main part of our project, so I will go into detail. As for the runner class, it is just a video generator. It can download every single step in every epoch, so that we can have an overview of the training process. Firstly, I'm going to introduce the mains. There are several choices for mains algorithm actually, but we have chosen the randomized Prim's algorithm. This shows the logic of Prim's algorithm. And this is the source code of this algorithm. You can see that there are 4 parameters right here. But what does it mean? What is complexity and density? You can see the explanation right here. With a low complexity, islands are very small and the maze is very easy to solve. With low density, the maze has small big empty rooms. And this is the running result of this algorithm. But how to use it? You can see that we can initialize a maze with the main size and trap number, and the final photos looks like this. But how to move the turkey and sense the location? Actually, there are two functions that can solve this problem. We can use the senseTurkey function to sense the location of the turkey, and to move the turkey with this function with a specific direction. Yes, and then we have tried to move the turkey in 10 times. And we can see that the turkey has been moved from the original location to here. And this is the direction and reward. Now I'm going to introduce the turkey class. The turkey class is the main part of our implementation. We have applied the techniques of reinforcement learning to train the turkey so that it can reach the Hong Kong UST logo in an optimal route. And there are several functions in this class. The most important one is the update function. The update function can describe the procedure what to do when updating the turkey. It is called every time in every epoch in training or testing. Also, it will return the current action and reward. But how to use it? This is the source code, and you can see that the turkey is updated and the turkey is moved with a direction of up. However, it bounced into the wall and get a reward of -10. And this is the implementation part of our project. Then my teammate is going to introduce the result.
Here comes to the results part. After we finish our work above, we can now run the code to train our turkey. What's more, we can select different value of parameters we talked before to find the difference of success times charts, accumulated reward charts, and running times charts. The main parameters we can adjust include chaining parameter, robot parameters, and maze parameters. This shows the output of the maze. We can get 3 charts below. Success times charts represent the cumulative number of times our turkey succeed in chaining. Accumulated reward charts stands for the accumulated reward value of our turkey in each chaining epoch. Running times charts represent the sequence of chaining in each chaining epoch. Here shows the different outputs of different parameters value we select. From the comparison, we can find that when epsilon and gamma fixed, if the learning rate alpha is bigger, the running time per epoch will decrease faster, which means the turkey can find the best way with less epoch. From the comparison, we can find that when epsilon and alpha fixed, if the discount rate gamma is bigger, the accumulated reward will grow faster and the running time will decrease faster and more steadily. From the comparison, we can find that when alpha and gamma fixed, if the epsilon is smaller, the accumulated reward will grow steadily. Finally, we select alpha equals to 0.5, gamma equals to 0.9, and epsilon equals to 0.1. Alpha equals to 0.5 because both the old Q value and the new Q value should be taken into account, so that the turkey can learn from the old experience while accepting the new experience averagely. Gamma equals to 0.9 because we want to make the turkey take fully account of experience of future steps. Epsilon equals to 0.1 because we want to make the turkey make a choice according to the highest reward, but we also want it to try different way randomly at the beginning when it has less experience. This is a trade-off between exploration and exploitation. This table shows the collaboration of our team. This is the end of our presentation. Thanks for watching.